And on to resonance. So we will periodically hear the question, why? Why did this thing happen? Why did that thing happen? The answer is usually resonance. And I used to say it was like 90% of the time, and it progressively dropped lower and lower, but we're still at least 50%, probably 60, 70% of the time, the answer is resonance for why something happened. Okay, so we really need to understand what's going on with resonance, when to use it, how to use it, and how it manipulates. So really what resonance is the ability to arrange a compound's electrons, but only their electrons, in more than one way of equal energy. Okay, so we encounter some issues with electrons, and we encounter some issues of equal energy. That equal energy we kind of addressed earlier. That's the best Lewis structure versus useful Lewis structures. And you'll find that we will oscillate kind of back and forth between that. Early in first semester, what you should be drawing for resonance would be equally best structures, so you can't tell a difference between them. As we move further on, you'll start trying to reference and draw out useful Lewis structures, because now you're concerned about how it reacts, not just the absolute of what it is. Okay, so let's get a feel for what's going on with it. So what electrons are allowed to move? Well, we've got a drawing down below, which does have resonance, so we could try and play around with it. And if we were to go through and look at it, we want to come up with some kind of labelings behind these so that we know what we're referencing and when we're referencing them. And some of these labels may seem a little bit weird, but that's because you don't understand why I'm picking these labels. We'll understand why when we get a better understanding of where electrons exist within a molecule. First, I want you to have some practice with drawing these things. So let's go ahead and identify the different types of electrons within this structure. So the first question would be, how many different types of electrons do you see within this structure? I would argue there's three. That's not quite a silly enough face of it. There we go. I would argue there's three types. We have one type, we have two types, and we have three types. Okay? And if you're curious about that labeling system, I'll go through and kind of color in all our electrons so you see how I'm differentiating these things. And so hopefully what you can see as types are kind of blue color would be our non-bonding electrons. Okay? And then where we run into an issue is that red versus that orange. And orange may not have been the best color. But we'll call that red color a bond. And the label that I'm going to choose for it is going to be an S bond. Again, you don't need to stress about why I'm picking that as a label. And then the orange one is still a bond, but it is distinctly different from the red bond because it's a second line on top of it. Okay? So that one I'm going to pick as a P bond. Okay? So we really have these kind of three classes of electrons. We could call them N for non-bonding, S bonds, and P bonds. All of those electrons are within our structure. So now we have to decide, do all of those electrons have an equal ability to move? Okay. And so one of the definition things that we need to keep in mind is that we have to keep the compound together. If for whatever reason we move the electrons and the compound no longer exists, well, that doesn't count as resonance because it's not the compound. Okay, so to that end, let's go ahead and take a look at the S bond. Okay, and we're going to start with the first S bond that I labeled. Whoops, that's excessively erased. I'm going to look at that one red S bond, and I want to see if I can move it. So I'm going to move both electrons because it just seems to be easier that way, and I want to decide where I want to move them. So electrons don't exist for long, so they can really only move short distances. So I can either move them from that bond, and I can only jump to an atom. So I could take those 2 electrons and I could put them on that atom. So what I'm showing with that arrow is moving those 2 electrons. If I did so, there would be our oxygen with those electrons, and then we'd have that pair of electrons on that oxygen. The bond that connected it to the carbon would no longer be present. Okay, and it would no longer be present because I took them out of the bond and put them on the oxygen, which means we have now 2 quote-unquote compounds, 2 different pieces, which means moving the electrons in that way, it's not the same compound. So that can't count as resonance because I'm having a different compound. Well, what if I'd moved those electrons the other direction towards that carbon? Well, the same thing would happen. I would lose that sigma bond, or lose that bond, that S bond, except now I'd be placing electrons on the other side. So again, it doesn't make sense to move the S bond, and we can see that here. Okay, we end up breaking the structure and breaking the compound. So S bond electrons not allowed to move. Okay, so that's useful. So S bond can't move, which means I don't need to look at that bond and I don't need to look at that bond. But I still have the non-bonding and the p-type bond. So let's take a look at the p-type bond because we're already starting on the bond path. And let's take those 2 electrons and we're going to move them towards the oxygen. Well, what would happen? I didn't do anything to any of the other atoms, so they should all stay the same. There's that oxygen. Oh, and really all of that should have been in black so that we can see that it didn't change. So we'll just kind of overlay that. And now we would have that extra pair of electrons on that oxygen, right? Do we have the same compound? Well, what makes it the compound is the connections between those atoms. Those atoms are still connected to each other. That's why we have the lines there. So yeah, I have the same compound, but I've changed the location of where those electrons are. So that by definition satisfies resonance. Okay? Best or useful, we aren't addressing yet. Could I have just as easily moved those electrons towards the carbon? Well, what would have happened in that case? Well, all the other atoms are staying the same, except now that carbon would have those electrons. Do we still have the same atom connectivity? Well, yeah, because we have that same connectivity, we have the same compound. So this could count as a potential resonance. So now let's push to the best versus useful kind of options. Really what we've done is just moved those electrons. So we have proven one thing, that p bonds can move. So that's good. And the s bonds cannot. Do both of these drawings, new drawings that I've done, make valid sense? Okay, does it make sense to do each of those? All we did was move the electrons, so there shouldn't be any real difference. In one case, I moved the electrons towards the oxygen. In the other case, I moved them towards the carbon. So we're taking bonding electrons and we're saying they could equally go both ways. Well, wasn't there a thing called electronegativity that dictated which atom would preferentially take electrons? Well, yeah, that was the whole point of electronegativity. And if we compare oxygen to carbon, oxygen is by far more electronegative than the carbon, which means if we look at this, the one structure is very preferential to the 2 structure because we're now supporting rules of electronegativity. Electronegativity is effectively this, I don't know what I was going to come up with there, let's say a law, and we don't want to break that law. So much so that structure 2 doesn't happen. That doesn't make any sense. So when we're moving our electrons, we do want to move them around, but we want to move them according to principles of electronegativity. And electronegativity is chi. That's the symbol we can use. So we want to use our principles of electronegativity. And this allows us to now show something about how they move. That means structure 2 is invalid, and we should really only be seeing what we're calling structure 1. Okay? Well, is structure 1 of equal energy to our structure 0? Well, to decide that equal energy, we should really be looking at formal charges. And if we go through to calculate formal charges, which I'm going to allow you to pause the video here and calculate for yourself, you should find that that oxygen is negatively charged, that each of our oxygens are negatively charged, but they were negatively charged to begin with too, and the carbon is positive. Okay? And if we look at our structure 0, the oxygen and the carbon were neutral. What does that mean? Well, that means structure 1 is higher in energy than structure 0, and if we were asked to draw resonance, structure 1 isn't really a valid structure to draw because it is higher in energy, okay? Or not a best. It could be a useful one because that now allows us to see something about the reactivity. That P bond could move around, generating a negative oxygen and a positive carbon. We now have sites of reactivity within the molecule. Cool. But it doesn't satisfy our equal energy. So before we get rid of that, what I want to go back and do is I want to reevaluate some of the other options for moving electrons, because we still had the non-bonding electrons, okay, our N electrons. Could the N electrons move? Well, let's go through and take an example. Could I take those N electrons and move them somewhere? Well, again, electrons can't move very far, so we're really only moving short distances. Our short distance would be to that bond. Well, what would happen if I did that? And I'll go ahead and include the charges down there. I did the same silly thing again. So if we drew that all out, again, trying to represent where those electrons were located, we would get something along these lines. I'd say, well, does that count as resonance? I have the same connectivity. The atoms are all connected. Shouldn't that count? Well, before we get too excited about saying it counts, let's take a look at the electrons around that carbon. There's 2, 4, 6, 8, 10 electrons. That's 10 electrons. Can I exceed the octet on carbon? Well, since carbon is in a second row element, we don't have access to the 3D orbitals, which means that structure or that movement not allowed. Okay? So when we're moving our electrons, we do have to move them in a way that is valid. Okay? We can't exceed octets. Okay? So we might say that our non-bonding electrons, our N electrons, can't move. But before we do that, we have to be careful and say, well, are all of those non-bonding electrons really the same? And I would argue that the non-bonding electrons on those other oxygens are different, okay? And they're going to be different because of hybridization, which we haven't talked about, because they're located on an oxygen that just has S bonds versus P bonds, okay? And if we looked at those electrons, we're still going to run into this issue of exceeding octets. So let's say they're actually all the same. Let's stick with that. This is what happens when we try and stumble across new processes. So we might say that those electrons aren't allowed to move. But we did draw a new structure, right? Structure 1. That new structure, we said, may not have been the best, but it exists. It's a valid structure. It's just not the same energy. Could we have applied moving the electrons on that new structure? Well, clearly we could have moved the electrons that we had just moved up, right? Okay. Remember, we took that P bond and we moved them up. Couldn't we have just as easily taken those exact same electrons and move them back down. Well, yeah, but that's not particularly exciting. That just says we undid what we already did. Could we have moved a different pair? And if we move that different pair, what ends up happening? Do we get the same atom connectivity? Yes. And interestingly enough, if we go through to calculate formal charge, we'll notice that this new structure that came from moving our non-bonding electrons has the exact same energy as structure 0. And really structure 1 was just an intermediate on the way to getting to structure 2. Okay? It was our showing of work. So when we're talking about moving our electrons, we have to be aware of what electrons can move, our p bond can move, and our non-bonding electrons can move. But there were things that allowed them to move or not. So first, we followed principles of electronegativity, and we also followed the principle of kind of octets. Okay, we had to be careful when we exceeded. Okay, so we had to look at octets. And in particular, if we looked at that octet, structure 1 maintained that kind of geometry, the connectivity, but we were under octet. Over octet, we said we couldn't do. Under octet. Well, under octet is bad too, isn't it? Well, yes, but not so bad that it can't happen. Okay, and we could actually make an argument that structure 1, never actually existed. Okay? Structure 1 is our work allowing us to see how this all came together. So now let's put it all together. What happened to structure 0? I took the non-bonding pair and I moved them. That then caused an exceeded octet on the carbon. So then what did I do? I took the p bond and I moved that up. So when we were moving our electrons, we could follow principles of electronegativity and octets. They're both actually tied together in the same general principle. When we were under octet, we could kind of leave that as a work structure. When we were over octet, we just kind of canceled it. Okay? Well, canceling things isn't the greatest move. Okay? So I actually want to take a second and go back and look at that exceeded octet and say that maybe the exceeded octet wasn't necessarily a horrible thing. Couldn't we have used that as a potential work drawing? Yes, we could have. Okay? So our exceeded octet, that was doing that. We could still use that as a work. So structure 1 was a work. Could we use the exceeded octet as a work too? And we'll call this 3 work. To get from structure 1 to structure 2, we had to move a non-bonding pair. The same kind of thing can be used with work 3. Is we could go through and say, well, we've now exceeded the octet. There aren't non-bonding pairs to move. So when we were under an octet, we had to move a bond, right? Because we had to get the electrons away from when we were under octet, we had to move electrons towards it so that we could achieve the octet. If we're over octet, we now have to move electrons away from it. So we're going to have to move different electrons in this case. The electrons we're going to have to move would be the electrons we were allowed to move, which would be our p bond. And so when we look at that exceeded carbon octet, what p electrons could we move away? Well, the only p ones we could move away would be those. And if we did so, what structure would we end with? Well, we'd end with structure 0. Right? So exceeding the octet with our electron move isn't necessarily a bad thing. Just like our under octet, we can use that as a work structure. Right? And as a work structure, we can say that we have something bad, we need to fix it. How would we fix it? So how could I go from structure 0 to a new structure that involved that work structure? Well, we'd move our non-bonding down, and then we'd move those electrons up. What's the net result? Well, the net result is that I form a new bond, still have the old one, and I got rid of that lone pair. We got a new lone pair, or the old lone pair is there, and then we have that one, then we have carbon, and we did nothing else with the rest of these. The net result is that I did nothing. We moved the non-bond down to make a p bond, and then lost a p bond. The net result was no change, which means those arrows don't make any sense to do, because we aren't drawing anything new, right? And that's where it becomes challenging. So when we're looking at our electrons, the big lesson is that we have two sources of electrons we can move, p bond and non-bonding electrons. They're allowed to move. In their moving, we have to consider octets. Right? Those octets, if we exceed, we have to use our exceeded structure to help us dictate how to move. If they're under, we have to use that under structure to dictate how we could potentially move to get other structures in. Right? So it's all about just trying to manipulate our electrons. Note that in each of these cases, we're using arrows to show how the electrons move. Okay? That becomes critical. The arrows are your work for the process. If you don't show that work, you don't know how to draw the new structure. And ultimately, if you're drawing a structure and then adding arrows, what you're saying is you know the answer. You might, if you memorized it. If you didn't memorize it, you're just making crap up and hoping for the best. Okay? So be careful when you're looking at resonance and try and focus on how you can shift and move the electrons around, because it's that movement that becomes important. Okay? So let's look at some kind of summaries. So which electrons are multi-bonds, or what I'm calling p bonds, okay, or we call p bonds, also known as pi bonds. We'll address that definition later. And are non-bonding pairs. Those are allowed to move. Okay? The s bonds can't touch those, okay, because those break the compound. And now how do those electrons move? Well, they move from bond to atom. So non-bond, or from a bond, p bond, to an atom. Or they move from an atom, a non-bonding pair of electrons, into a bond. And that's it. Those are the only two ways you can manipulate them. Okay? So, rules of resonance, put it all together. We need to find a source of electrons. That's our multi-bond or non-bond. And move electrons to the immediate vicinity. Okay? There's our two rules. Now we have to look at our octets. Okay? If we have too many electrons, we have to break a multi-bond or pi bond by moving electrons. If too few electrons, we have the potential for a Lewis structure. Okay? Because we can be under, we can't be over. Over is wrong. Under, maybe. Okay? So we have the potential for a structure, compare it to your starting structure, or repeat step 2 and just kind of continue to move. Right? So we've got another structure down below, benzene. What I'd like you to go through and do is see what you can come up with. Right? So this would be the opportunity to pause again and see if you can address how those electrons move through the structure. You didn't click pause, did you? You're waiting for me to draw something. You should click pause. Okay, let's go ahead and look at it. I'm going to assume you've come back and you've drawn it. Okay, so here we go. Find a source of electrons. Well, there's no non-bonding electrons here. I can only pull p bonds. Okay, so I'm going to move from a bond to an atom. So I'm going to go from that bond. The only atoms that are here would either be that carbon or that carbon. I can move them either way. It really doesn't matter. Okay, and that's because there's symmetry in the molecule. So I'm going to move them this way. Okay, the result of that, we'll see why I've got to draw this small in a little bit. Draw on all our hydrogens. Would now be that lone pair on that carbon. Okay, and remember we have We have to show that lone pair. The structure is still wrong, and that would be wrong because we now have to consider formal charge. We had a bond that made everything neutral. We took those electrons in that bond and we put them all on one carbon. Right? So if I compare, we'll call it our red dot carbon and our green dot carbon, that red dot came in with 4 valence electrons, minus 3 bonds, minus 2 non-bonding. This gets me a -1. That green one came in with 4 valence electrons, minus 3 bonds, minus, well, there's no non-bonding electrons. And great, I've lost connectivity and none of that is being drawn. Came in with no non-bonding electrons, which means it's 4 minus 3 plus 1. It would be a positive charge. Okay, well, that becomes problematic. Okay? Or not necessarily problematic, something I would have to label. If we consider our octets, the red carbon, by the way, if you're wondering why I'm not drawing anything, I'm waiting for my thing to reconnect here. The red one, oof. Let's see, is it working? The red one is a -1. Yep, we're back. And then the green one came in as a positive. Well, the red one is as a negative. We may not like a negative charge, but it isn't an exceeded octet because we still have 8 electrons around it. The green one is missing an octet, so that is problematic. Okay, so how would we fix that? We would need to move electrons towards it. Well, we could do that by moving those back. But if we did so, we undo the process that we just went through and did. So that's, oh my God, good grief. Okay, so everything just got deleted on my end, so I'm gonna have to redraw that. So while I'm redrawing that, we need to decide what we can do. Okay, and at this point, we're really kind of gonna have to invalidate all of the rules, or not necessarily all of the rules, but invalidate all of the kind of steps that we've taken already. Because we said if we had that positive charge, we needed to fix it. Okay? Well, we're actually going to say, you know, I'm just going to let it go. Sometimes you just got to be like Elsa. So what do we got to do? Okay, I don't have a way to fix that positive charge that doesn't generate a new resonance. So instead, I'm going to say that negative things are bad. Let's try and fix that. So how could I move those electrons? Well, I could take those from the atom and move them to the bond, right, to that hydrogen. And if we go through and do that, what do we notice? Oh, for the love of God, it's losing connection again. Well, in the hopes that it actually works, we would exceed the octet to that hydrogen. Hydrogen can only have 2 electrons around it. That becomes problematic for us because if the hydrogen doesn't have those or has exceeded its octet, we're not allowed to draw it. So what we would need to do would be to fix it. And the way we said that we could fix an exceeded octet was to move the p electrons. Well, the p electrons are currently right next to it, okay, or that are connected to it. So what do? We could move those electrons away from the exceeded octet, which means right back to the carbon. The result is that we get back to the red structure, which means moving the electrons the way that didn't actually get drawn out, moving the non-bonding electrons to the bond between the carbon and the hydrogen was actually not useful. Okay, so that didn't work for us. It's not bad that we tried it. That just means that we hit a dead end. That just doesn't work. So what we'll do is go back to our drawing and say, well, where else could I move those electrons? Well, we could try and move that non-bonding pair of electrons into there. Okay. The result, and because now we've seen that we can't draw to the hydrogens, I'm going to start implying the hydrogens. No, I'm not, because we need to see our octets. That we would have this drawing, right? And we haven't touched that positive charge, so that's still chilling out there. Hopefully what we see, that carbon has exceeded its octet. So this is again a bad drawing, okay? But we can use this drawing to help us. We've exceeded the octet. Do we have p electrons that we could move? Well, we do have the p electrons that we just moved in. Well, that would be silly just to put them back because that undoes it. So what we want to do is try something new. Do we have some other p electrons? Well, yes, we do. We can move those there. I'm drawing that arrow on a structure I'm not allowed to have because that's an invalid structure. So what I will have to do is draw that arrow back on the red structure. Okay? That arrow has to show up in the red structure because if I didn't have it there, I would be drawing the blue structure and saying it exists, and it can't exist because we've exceeded an octet. The net result, hydrogen, hydrogens, I hate drawing hydrogens, hydrogen, hydrogen. We'd have the negative charge down here. We'd have our double bond now there. We'd have that negative, and we would have that as a drawing with our positive charge up here. Okay? And we've got yet another drawing, equal in energy to our red one, but not as good as the black. Okay? Well, we could try this again. Okay? For those of you paying attention, hopefully what you note is that if we use that red arrow, we would exceed the octet of what I'm now going to call that blue carbon. So we would also have to add another arrow to shuttle the electrons there. Okay? This is now going to result in, why not? Let's go ahead and show a blue structure. Throw on all our hydrogens. There's the red double bond. Oops. There's our old blue double bond. And then we would have the negative charge here. We still have that positive. Okay. Now what could we do? Well, we could throw that negative into that. And the result of all of that, we're now going to have to go up. I attempted to draw it small, and then the computer futzed up on me. And I got frustrated and started drawing everything big. Is we would end with that, right? Is that black structure that I've just drawn better than the blue one? Well, yes, it's not charged. Is it better than the orange one? Yes, not charged. Better than the red one? Yes, not charged. Is the black structure that I've drawn better than the black structure that we started with? No. Are they different? Yes. The double bonds have alternated to different positions. What we drew through our rainbow of colors was effectively intermediate resonance structures, allowing us to move from one black structure to the other black structure. And in that motion, hopefully what you noticed is that we were able to move non-bonding electrons and p bonds. And if we looked at that process all the way through this, what we might note is that we could have taken that bond and we could have moved it here. And then that orange bond, we could have moved it here. And then that red bond, we could have moved it here. And note what we've done with those new arrows is we didn't move bond to atom, and we didn't move atom to bond. We moved bond to bond. That bond to bond is a very close bond to bond. Okay, it is not bond across the molecule bond. It is bond atom bond. Very short distances. That allows us to be able to kind of add a third rule into this that simplifies our arrow pushing and can make our life a little bit easier when dealing with resonance, assuming our computer works all the time, right? And that is what is in that little grayed out box, moving from bond to bond, okay? So when dealing with resonance, use your curved arrows to kind of move electrons. This is a work process. This is showing calculations. Drawing the structure that results from it isn't necessarily a bad thing, but the only way you can draw that structure 100% correct is if you know the answer. And if you don't know the answer, which you probably won't, you're going to get things wrong. Okay? So work on this process of how you move those electrons, and that's going to help you out. In the recommended list of books, there's a book by Weeks called Pushing Electrons. That's exactly what that book does. Okay? It's a problem-solving book where all you do is move electrons, because what you're trying to get used to is that process. Those of you saying, well, dang, it's resonance, we don't have to worry about it. This is literally what OChem is, moving electrons. Right? Except we won't do it where we just move electrons within a molecule. We'll move electrons between molecules to make new things. Okay? So you really need to understand this process. These are the basics of the rules. Now it's a question of application. Okay? What can happen is we can throw in new structures. Say if I gave you this as a skeleton with that positive charge, note there's no electrons shown here because I expect you to know your Lewis rules and how many electrons should make it into this drawing. What you should then be able to go through and do is draw all of the Lewis structures to represent this molecule. Okay? That is a challenge, but you should be able to go through and do it. It's relatively minimal because it's just counting electrons. You've got a structure already built out. You should spend the time to see what you can come up with as potential answers. To give you a hint for your answers, you should have 3 structures. Okay? After that, we're now really kind of at the end of our Lewis structure realm. Okay? So what you need to be doing is looking for these patterns. It's not just drawing Lewis structures, but it's identifying patterns. One of those patterns is identifying the charges and the number of bonds on happy structures. Okay? So a neutral structure, if it has boron, will have 3 bonds. A neutral carbon will have 4 bonds. A neutral nitrogen will have 3 bonds and a lone pair. A neutral oxygen, 2 bonds and 2 lone pairs. Okay, so recognizing those patterns can really help you out so that when you see a structure, you can be like, that's not right, okay, which means that's probably not the right multiple choice answer. Okay, or you could look at it and be like, oh, I know how to manipulate that structure to get to a better one. Okay, so these patterns are things that are important for you to be looking for and trying to identify through your practice. If you decide to not do that practice, that's also okay. You're memorizing this slide. Right? And really just saying, well, it's only 4 things. It's not a big deal. That's 5 things. Not a big deal. You also have to memorize what happens if it's positively charged. What happens if it's negatively charged? Okay? That's just basic building blocks. The next step is how do you build those building blocks? How do you build with those pieces? Okay? So again, I'd recommend doing the practice so that these patterns become obvious to you and you know where they're at. Okay? But that's ultimately the point of practice, is to get to these patterns. Once you have these patterns, you're pretty well locked down. Okay? With that, yep, that's kind of an important lead into the next section. Is the shape of the molecule going to change the interaction? Yeah. Do Lewis structures actually represent shape very well? No. And that's why we had that Vesper theory that we're going to look at here in the next video, hopefully in a whole lot less time than 40 freaking minutes, which I'm blaming the computer for.